Alright, so this is lecture 15 on the CMOS scaling. So far we have talked about the semiconductor device physics, like we introduced the electron and holes, and then we talk about the basic built-in devices, like the PN junction, MOSFET, and then we discuss the circuit made of those devices. For example, here we use inverter as a basic digital circuit block to discuss the circuit performance, like the delay and the power and energy. So we have talked about those circuit performances. And then today we are going to have further discussions on the CMOS scaling and its impact on the circuit performance. And this is lecture 15. And this is the recorded lectures from the Professor Asif Khan. So let's look at this MOSFET scaling trend historically. I think we have shown this chart at the very beginning of the semester when we talk about the scaling. So here this chart shows the gate length L as a function of the generations over the years. So from the 1970s, 3 micrometer node to here 2008, 35 nanometer, and today is 10 nanometer or 7 nanometer as of 2020. So this is the exponential decrease of the gate length L over the years. The reason we use L as a metric because it is the minimal feature size we can have for a particular technology node. So this is the smallest dimension in the transistor. And this is limited typically by the lithography of the technology node. And if you want to visualize the scaling, here we show the transistor structure proportional to the scale. So this is at 3 micrometer. You have this kind of transistor in this kind of dimensions. And in today's here, I think this is around 14 nanometer node. The transistor is as small as this. So you see how aggressive this scaling is over the past 30-40 years. So you can make this transistor so small, so you can pack more transistor on the chip, and this is the power of the Moore's law. We have discussed the Moore's law at the very beginning of the semester. So the Moore's law, as we introduced, it was predicted by Gordon Moore, who is a co-founder of the Intel, and he predicted back in the 1960s. He predicted that the number of transistors in a dense integrated circuit doubles approximately every 2 years per generation. So the number of transistors double, or in other words, the area per transistor shrink to 50%, half of the previous generation. So that translates to the reduction of the size of the transistor. Let's say if you think about the reduction of the area by 50%, that means the size, let's say, reduced by 0.7x. Because 0.7 times 0.7 will give you 0.5, roughly 50% reduction of the area from generation to generation. And here, this is an interesting article written by Gordon Moore in 1998 to review the historical trend, which he predicted 30-40 years back. So if you're interested in this, you are encouraged to read this article from this link. So here the Moore's law only talk about the number of transistors on the chip, or let's say the density of the transistor doubles, and that will translate to the reduction of the cost per transistor. So if you double the density of the transistor, make the transistor smaller, then on the same chip area, then you are going to have more transistors. So the cost per transistor will reduce. So this is the driving force for the scaling to lower down the cost. But there's another scaling rule we are going to discuss in more details today, called the Dennard scaling law. So this one not only predicts the number of transistors, but also talk about the power density in the chip and also the clock frequency in the chip. So here the conclusion is that the transistor will get smaller as we scale. Meanwhile, the power density in a chip will stay the same. Power density is, let's say, measured as the power divided by the chip area. And then the clock frequency of the chip can increase with the scaling. So this is predicted by Bob Dennard in this article back in 1974 in IEEE Journal of Solid-State Circuits. And this is the original paper, the title, and the authors. So we're going to discuss the Dennard scaling law in more details today, because it talks about the circuit performance, like the power density and the clock frequency. And here we show this Moore's law again. So this is the Golden Moore, and this is his famous prediction. And here is the historical trend of the transistor count, number of transistors on the processor over the years. And you see this is an exponential increase of the transistor because this is in log scale. And most of the chips here are from Intel, but you do see some of the AMD chips as well. So this transistor count doubles almost every 2 years, and this is incredible for the economics of this semiconductor industry. But we see that the Moore's law is going to slow down. Actually has already been slowed down in the past few years. So from generation to generation, nowadays it's not 2 years, maybe 3 years, and in the future maybe will be 4 years, because we are reaching the limit of the physics. As of today, the transistor gate length, as we showed before, like this 10 nanometer, and the atom, silicon atom, we talked about that before. The atom size is about 0.3 or 0.4 nanometer. So from the source to drain, you only have like 20 atoms. So we are reaching the limit of the physics. And this is historical trend. And the Moore's law is more economics driven, because the driving force for this one is to reduce the cost per transistor. So you make the chip cheaper and cheaper. So this is the Moore's law. Any questions so far? So if you want to ask a question, please unmute yourself or use the chat function. If no, we will continue. So here are more articles regarding the Moore's law. If you are interested, you can read those papers or articles. But today we are going to spend more time to discuss this Dennard scaling rule. So because this is more physics driven, and let's talk about the Dennard first. So this is Bob Dennard, and he is also famous, not only because of this scaling rule, but also he is the inventor of the DRAM technology. So you have used that every day in your electronics, like your smartphone, your tablet, your laptop. This DRAM, this RAM, like 4 GB, 8 GB, this is invented by him as well. He is a fellow of IBM, and he has been working in IBM for the past 30 or 40 years, and now he is retired. So he predicted this scaling rule in the 1970s. So let's have some statements from this Dennard scaling. So I will read this through, and I will discuss those statements in more details in the later slides. But let's read this through. So according to the Dennard scaling, the transistor dimensions are scaled by 30%, or equivalently, we are doing this 0.7x per generation. And the area of the transistor will reduce by 50%. So far, this is still the Moore's law, right? Moore's law only talk about this transistor count or the dimension of the transistor scale. But the next is what the Dennard scaling rule tells you. So next here, this reduces the delay by 30%, or let's say 0.7x. Therefore, increase operating frequency about 40%, or become 1.4x. So this is one of the indication of Dennard's scaling rule. This is regarding the delay or the frequency of the circuit. And then to keep the electric field constant, the voltage needs to be reduced by 30%. So here the voltage, for example, the power supply, VDD, needs to be reduced by 30%. So this will reduce the energy of the circuit by 65% and then reduce the power at the 1.4x frequency by 50%. So therefore, in every technology generation, the transistor density doubles, circuit becomes 40% faster, while the total power consumption with twice the number of transistors on the chip will stay the same. So this is a statement, and we will discuss how we reach this kind of conclusion in the following slides. So basically here we talk about the first delay and secondly the power. How would those two metrics change with the scaling? So let me break the video to